Does anybody have any objections to me passing the mini exams back out?
I do.
You do? All right, then y'all pick them up after class. There's no grades. There's no grade. I mean, there's no grade on the exam.
I was just objecting because you said the same would object. So.
Oh, do you object?
Yeah, I just figured I'd be that one guy.
Do you still object?
Possibly, I don't know.
Yes? No? All right. So y'all get them after class.
Oh, what? I said no.
You do object or you don't?
I said I don't object.
You don't object?
I repealed my objection.
Oh, okay. I didn't hear you repeal. Anybody? So everyone's okay? Everyone's okay? Yes? Okay. Well, because if one person doesn't want their test to be seen by other people, I'm not going to pass them around. So, man, shit, when I was in school, they'd hand them out in order from highest to lowest. You know, and it's just like,
That's terrible. No, I think that's
you think that's bad? I mean, I think that's some incentive to not be the last one on the list.
No, I agree. I think it's fun.
There's no like.
Is that thing in the door? Oh, here we go. There we go. All right. You have a mini exam due on Wednesday, right? There's another one due on Wednesday if you're doing it, right? Remember, you only have to do 2. I mean, sorry, you can skip 2. Sorry, you can skip 2.
That fundamentally changes.
Yeah, that changes everything. And then I'll have one more for you. All right, I'll have one more, maybe 2. We'll see. All right, so where are we in terms of timeline? We're supposed to start fundamental theorem of line integrals today. We are going to do that, but I want to wrap up the line integrals from last class. We had 2 more examples to do, and then we're going to get into the next section, and then we'll just see how far we go. All right, so we were here, and man, I really don't want to take too much time, but I think it's important enough for us to look at this note. We were doing the silo, the person going around the silo. Remember that problem? 200 pounds, whatever. Let's pause on that for a second. So we learned this notation class or 2 ago. It's basically like the work integral. It's a line integral over some curve C. You have your vector field dotted with the derivative of your curve function. That's basically what this is. And this is to show you that this is an equivalent notation for the same exact thing. And I'm going to be switching between these notations throughout the next few class meetings. We only have 6 more class meetings, and then we have a final. So, so what this says is that if your vector field that you're given has 3 components, or this works for 2 components as well, we'll call the first component function P. P would be a scalar function, and then Q would be a scalar function, and R would be a scalar function. You have the 3 scalar functions P, Q, R, that if you want to do the work integral, what you do is the line integral of the P with respect to X, then add to that the Q with respect to Y, and then the R with respect to Z. So those, you'll see me use that in a little while, so when you're lost and don't know what I'm doing, this is where I'm telling you what I'm doing, all right? All right, let's finish this problem up. We had this person, 180 pounds, carrying 20-pound bag, is going to go up a helical staircase wrapped around 20-foot radius cylindrical silo. It takes 3 complete revolutions to get to the top. How much work is done against gravity? So those of you who've taken a physics class knows that if you're going to move an object vertically, just vertical displacement, then the work done is just what? The displacement times weight of the object. That's it. So our answer here should be the weight, which is 200 pounds, moved how far? Vertically, 90 feet. So 180 foot-pounds should be our answer. If you take a physics class, it's vertical displacement is very simple to compute. So you might be saying, well, why are we doing this? Wait till the next example, because then on the next example, it's not just vertical displacement, and we're not on Earth. So we need a more general formula. And so this first example is simple to solve, but we really want to understand what we're doing, all right? So my picture here is a cylindrical silo. It has a 20-foot radius. It's 90 feet tall. And we're going to start at some point, and it's like a helical staircase that goes around, goes around the backside, comes up, right? And it should take, what was it, 1, 2, 3 revolutions. 3 full revolutions. Actually, I shouldn't be there. I should be back here. You get the idea, right? 3 full revolutions to get to the top, right? So I'm going to first start with the vector field because we want to calculate work, right? Work will be the integral over the curve C of the field dotted dr. So I need the field, right? The field is the force. And since gravity, we said, was the only force, we don't have any force in the x direction or the y direction, just in the z. So I think I put 0, 0, 200, right? And we talked about maybe we could put 200, negative 200. Depends on how you want to look at it. I'm going to put 200 here. All right, so that's our force. Now we need the actual curve that draw. Is there a question? No. Itch. Okay. So we need the actual vector function that draws this curve, right? We need it. So this is going to be our C, and we need it. We need to come up with that, and that's where we were. So the vector function, I'm going to say r of t is equal to, we first said that in the xy plane, if you're looking straight down, right, from the top down, it would just look like I'm drawing circles over and over, right, over and over. So I'm going to, oh, why did I put a comma? 20 cosine t, 20 sine t should draw me circles with radius of 20. And that would be, one circle would be 0 to 2 pi, right? I need to go 3 times around, so I'm going to let my t vary here between 0 and 6 pi. And that way I will draw the circle 3 times, right? Any questions here? Now, in terms of my vertical displacement, there's so many different ways to look at it. I told you if you unwrap the staircase and just stretch it out, it just looks like a line, doesn't it? Mm-hmm. And so if you look at it that way, this would be like the point 0, 0. So at time equals 0, you haven't gone anywhere. And then over here, this point would be, well, time is going to go from 0 to 6 pi. 6 pi would be like the x coordinate, but this is really the t coordinates, the measurement of time. 6 pi takes you to here, and then how high do we need to be? 90, right? And so now I've just kind of come up with an equation for that line right there. And so you have 2 points, right? It's a line, so it would be rise over run. So this rise, 90, take away 0. Rise, 90, over the run, 6 pi, over minus 0, which would be 6 pi. That's the slope of that line, right? And we need that to be linear in the function t. So when t is 0, right? When t is 0, we want this to be 0. And when t is 6 pi, we need that to be 90. So if I just multiply by t, that is the linear function that gives me that line. Does that all make sense to everyone? I'm not using x because t is our variable. Do you all agree that if I plug in 0, I get 0? Mm-hmm. And when I plug in 6 pi, I will have risen to 90 feet. 6 pi here, it cancels, you get 90. Okay, so that's going to be my z component of my position. Like that. Okay? There it is. All right, now let's calculate the actual work integral, right? So what we need to do is take the derivative of this, right? I need the derivative of this position. Let's go ahead and put that right over here. Squeeze it in right here. The derivative of that will be pretty straightforward derivative, negative 20 sine t, 20 cosine t, and then real nice, it's just a constant, 90 over 6 pi. So what I'm going to do is I'm going to take the field and dot it with that, right? Take the field and dot it with that. Now, when we say take the field, what I mean is take this field, and then if there were x's and y's in here, I would need to replace them with my position functions. But my field has no variables in it, it's just constants, right? So I'm just going to take that field and dot it with that. And that's all, and that's it, and then I'll just compute that integral. So the work will be the integral. Now I can put limits of integration, 0 to 6 pi. My field, 0, 0, 200, dotted with the derivative of the position function. dt. And for our physics people in here, do we see why now? Do we see why when you're dealing with gravity that your x and y positions don't matter? Because if you're dealing with gravity, these are always zeros, aren't they? And therefore, these two component functions are irrelevant. Because when you dot them, those are going away, aren't they? All that's really going to matter is this and this multiplied together, right? That's all that's going to matter. Yeah, let's move it in here. So we have work will be integral 0 to 6 pi dot, that's 0, and then plus that times that. What is that? 1800? 18,000 over 6 pi.
Couldn't we divide that 6 out to make it just 3,000 over 5?
Yeah, reduce the fraction. Yeah, absolutely. Yeah, and no t's though, right? Like that? Yes? And then what now? Integrate, right? So I'm just going to leave it. I'm not going to reduce. The antiderivative of that is that. Just to add the t, right? That's it. And then we go from t equals 0 to 6 pi. And plug in 6 pi, and the 6 pi cancels. That's why I didn't reduce it.
Yeah. I saw it.
Okay.
Once I looked at the integral.
6 pi goes in here, cancels out, you just get the 18,000. And then 0 goes in there, you get 0. So this is it, 18,000. And then work, because we're measuring things in feet here in pounds, this would be foot-pounds. Do you know what the other measurement of work is, the other standard unit? Joules, kilograms per meter squared over second squared, so joules. But here we're dealing with feet and pounds, so it's foot-pounds. 18,000 foot-pounds, which is exactly 90 feet times 200 pounds, okay? All right, that problem, again, pretty straightforward because we're just, vertical displacement against gravity. Whoa. But what about this problem here? You have an object, a 10 kilogram object. Okay, let's talk about this. Kilograms and pounds are not the same thing, right? A kilogram is a measurement of mass, and mass does not account for gravity at all, right? Or your weight is different than your mass. So your weight depends on what planet you're on. Your mass is independent of where you are in the universe. So when we measure things in kilograms, we're talking about mass. So I've given you the mass of an object, right? 10 kilograms. And it's moving with this position function. R of t equals sine 4t, sine 8t, t squared. That is a three-dimensional vector function, so I'm moving in a path in three-dimensional space. I am not saying in this problem that you are on Earth, okay? So we're not saying that there's a gravitational force. So this is almost like just something out in space with no gravity impact, affecting it. And so what we're asked to find is the work, right? We're asked to find the work. So let me just write down what we're given here. We're given the mass, right, is 10 kilograms. And then we're given r of t, which is the position function, right? And we're supposed to calculate the work, which is line integral over c of the field dotted dr, right? And the field is like our force, right? The force. We are not given the field, are we? We're not given the field. But we can get it, all right? Because what we are assuming is that this object is moving somewhere in the universe, just without gravity. So I'm going to go back to Newton, right? Newton's famous formula. Force equals mass times acceleration. Force is mass times acceleration. And this is a formula that you may or may not know. I'm sure you've seen it in your life. This formula works regardless of, this A could just be one-dimensional or it could be an actual vector. You can have acceleration vector and then your force becomes a vector as well. So that force is actually our field that we're going to be using here. And in order to do that, we need to take the mass of the object, which we have, and multiply it times the acceleration of the object. But do we know the acceleration of the object? Exactly. We have the position function, right? We can take its derivative to get velocity, its second derivative to get acceleration. So we're going to take the second derivative of this to get acceleration and put it right here. And then we will have our field. Once we have our field, we will dot that with the derivative of the position function, which is right there. See? So we're going to say that our field, let's take some derivatives. Let's do that. From here, what is r prime of t? So I need to take that derivative, take derivative of this. Be careful with the chain rule there. We're going to get a 4 to pop out. So 4 cosine 4t. And then we have 8 cosine 8t. And then we have 2t. Right? This is our derivative of our position. You could say that's velocity, couldn't you? Mm-hmm. All right. So I'm just going to put out here, this is my velocity. And then my acceleration is the second derivative. So take derivative of the position twice. And that will give me a negative 16 sine 4t. And then a negative 64 sine 8t. And then a 2. Y'all with me? All right. So now, let's write down the field. The field that we're working with here is going to be the mass times the acceleration, which is 10 times that acceleration function. Let's just do it. If I multiply this by 10, I'm scaling that by 10, right? So this becomes negative 160, negative 640, and a 20. So negative 160 sine 4t, negative 640 sine 8t, and then 20. That's my field.
So it's decelerating.
Yeah. I think we have everything we need, don't we? We have the field. We're going to dot that with the derivative of position, which is the velocity. We have that. And we're going to integrate from, well, they gave us some restrictions on time here, right? 0 to 1. All right, set it up. So integral, 0 to 1. Take all of that, negative 160 sine 4t, negative 640 sine 8t times 20. Dot that with this, 4 cosine 4t, 8 cosine 8t, and then 2t. Just make sure you're grabbing the velocity function, or the derivative of the position there. Don't accidentally grab the position or the acceleration again. We can dot those vectors, yes? I worked this out earlier because I didn't want to have any arithmetic mistakes. So this will be, let's see here. Yeah, okay, so this should be integral 0 to 1. We should have negative 640 sine, oh wait, no, yeah, sine 4t cosine 4t. And then we should have minus 5120 sine 8t cosine 8t. And then finally plus 40t. Yep. dt. All right, no more vectors, right? Now it's just scalars. And did I do the rest? I don't think I did. Oh, I did do the rest. Let's go ahead and let's finish it. May as well. It's not that bad. How do you do these integrations? Like, how would you do that? Basic U sub. What would you let U be? Some of you might use cosine. Some of you might use sine. It depends on you. I would use sine. Let U be sine 4t. Derivative of that's 4 cosine 4t. So I have to scale it, and right, just a basic U sub. Same thing here. Basic U sub. And then here, just power rule. Yeah? Can I just show you what it becomes? Okay. All right, so that becomes now one, wait a minute. Oh yeah, because there's a chain rule, and, oh, hold on. Yeah, antiderivative. So 160 cosine 4t, and then plus 1280 cosine 8t, and then plus 20t squared. And we evaluate that from 0 to 1. And I get an answer of 20. Yes?
Why wouldn't it be cosine 4t squared or cosine 8t squared?
Squared?
Yeah, because chain rule, right?
Well, what's the derivative of that? Negative sine t, negative sine of 4t times 4, right? So then hit that with a 4, and that becomes that. And then you still have the chain rule, so. All right. What's the derivative of this? Yes? You sure? Okay. You sure? Not that it's, is that an agreeable sure, or is that a sure? Yeah? Yes? Okay, so no, that was a question for you. I didn't include the units. So why, can I put units in here or not? I cannot. Because my position function, I'm not telling you like any measurement of distance there. So if I'm going to use joules, I have to be in meters. And I don't know what my position, this could be giving me, you know, like when you plug in 0, right, you get an answer 0, 0, 0. When you plug in 1, what do you get? Whatever sine of 4t, sine 8t, t squared is 1 squared is 1. So you get some vector. If you want to know how long it is, well, what are our units, right? Could be miles, could be light years, right? So without units, I can't really tell you what the actual SI unit, standard unit is for it. Yes?
We don't even necessarily know that those are seconds that we're counting either.
That's right. We don't know if those are seconds or hours or years. So this is a unitless answer right now. I would need more information to be able to put some unit on there. All right? Okay. We move on. Oh, that's it. This section's done. We're done with line integrals. What I would like to do while I've got this up here, I would like to just go back through again 13.2. I have a formula sheet, I believe, in the notes for the class. I want to just look at all the formulas for 13.2 again and just kind of make sure we have a general idea of what they are. Because there was a ton of stuff in 13.2. All right. Yes.
For the final,
Yes.
do we need to print this formula?
Yes. If you want to use them. Yeah, if you want to use them, you need to print them. I won't provide them, but you can bring them. And there's a bigger one. I think there's a 16-pager in there too. You can have all of it. Okay, so here's what we had in 13.2. Line integrals over curves in two-dimensional space. This was a notation. It was a scalar function here with respect to arc length. There's your vector function, there's your scalar function evaluated along a parametric representation of your curve, and then the arc length of that curve. Ooh. Then we said there's another one that's kind of a special case. That's the area of the curtain drop down, right? Then this is like a different case where we cast a shadow and get an area of a different curtain, and that's this notation. Then we cast a shadow on the other plane, and that's this integral. Then this was just notation. We said, hey, we can, whenever we want to do two line integrals like this, we can just write it like that, and we all know we mean the same thing. And then we talked about changing direction. If you change the direction of a line integral, it changes the sign of the answer. That's if it's with respect to x, and with respect to y, it changes the answer. But if you traverse the path in the opposite direction, if you're integrating with respect to arc length, then the sign does not change. Then we said, let's talk about the whole thing again, but in three-dimensional space. So you have a scalar function, right? Scalar function with respect to arc length. Here it is again. We have to find parametric representations of the curves, right? And then we said, well, you know what? Instead of writing that, this curve we draw, let's call that r of t, the vector function, r of t. And let's write this, the scalar function evaluated on the curve, on the vector curve, that will mean this. And then this is just the magnitude of the derivative of the curve function. Right? So that was just an alternate notation for that line integral. And then we had special ones with respect to x, then with respect to y, then with respect to z. And then notation, combining them. And then we moved on and we said, okay, forget line integrals. Okay, line integrals over some curve C where the function was scalar. Let's now let the function be a vector function. So we defined work. This was our work integral, which is what we just did 2 examples of, right? And then this is the big one that I started class with and I'm ending this section with. When we see this work integral, it's the same as this integral. So a work integral can turn into line integrals where your p, q, and r are your scalar functions within the vector field. So your first component function is p, second is q, then r. So we are going to use this now in the next section. That's it. So 13.3. All right, so you remember in Cal 2, end of Cal 1, beginning of Cal 2, you learned the fundamental theorem of calculus, right? The fundamental theorem of calculus. There's a fundamental theorem of algebra as well, but the fundamental theorem of calculus is like the thing we've been using for a long time, right? Now we have this new thing called the fundamental theorem of line integrals. And let's see what it says. It says if C is a smooth curve, all right, so we've got another curve that we can draw with a vector function, where we've got limits, right, a and b that draw that curve, so it starts somewhere and stops somewhere. And we have that this function f, the scalar function, or we have a scalar function. Yes, we have a scalar function f that's differentiable. That function can be a function of 2 or 3 variables, doesn't matter. Such that the gradient of that vector function is continuous on C. Just means that we don't have any problems, any discontinuities, any asymptotes or anything like that. Something that causes division by 0, where it would be undefined. As long as those conditions are met, then we have the following. The line integral over C of the gradient of f. Now the gradient of f, remember the gradient of f is a vector, which means this is like a capital F, right? This is like a capital F. So that's like work, right? But the condition is that that f is not just arbitrary. It's the actual gradient of some scalar function. So if we ever want to know what the line integral over C of the gradient of some scalar function is, dotted dr, which is the derivative of the position, all we have to do is evaluate the scalar function at r of b, subtract from it the scalar function at R of A. So I'm going to try and show the analogy of this in Cal 2. In Cal 2, we do this. Normally, we write this. This is the evaluation theorem, which is one version of the fundamental theorem of calculus, right? It says that if you have a function here and you find its antiderivative, then the area under this curve will be equal to evaluating the antiderivative of that at B and then subtract from it the antiderivative of that at A, right? That's what the fundamental theorem says. If I change the notation slightly here, let's change this, and instead of writing that and that and that, let me write little f here, then what would have to go in here? Well, yes, over there, but here, this would be f prime of x, wouldn't it? Because whatever's in here, you need to find the antiderivative over here, right? So if I'm calling this little f, then inside the integral has to be f prime, right? That's this. Do y'all see that here, right here, in this theorem? You've got basically the same idea, except that your scalar function, right? Your scalar function is now a function of more than one variable. And the derivative of it is going to be the gradient. That's how we're going to define the derivative of that scalar function. And then this is basically like a distance, all right? Which is kind of like the dx was. It's similar. It's not exactly the same, but it's very similar. You see that it formats almost exactly like that? All right, so let's do an example. Oh, I say something here at the end that do y'all remember what it means for a vector field to be conservative? What's that? Yeah, it's the gradient of some scalar function, right? So this theorem is saying that the line integral of a conservative vector field, that means a field that comes from the gradient of some scalar function, is simply the difference of the value of the scalar function f at the two endpoints. Further, the line integral on any two paths that connect the same 2 points are always equal if the field is conservative. This is a big point right here, because what we're saying is if I have some curve C, right, and this is the vector function at A, this is the vector function at B, we already saw that when you do line integrals, the path matters, doesn't it? The path matters. But this is saying that if you do the line integral, right, if this is a conservative vector field, if it's conservative, then all that matters are the two endpoints, because you're going to evaluate at the two endpoints, aren't you? So the path will not matter. You can go this way, you can go this way. Okay, it doesn't matter which path you take, as long as you start and end at the same place, the value of that line integral over that field is going to be the same exact answer, so long as the field is conservative. All right?